Hi everybody. In this video, we're going to look at cloud native Java. We're going to look at things that you can do to lessen the impact of building distributed systems that are intended for the cloud. A lot of us are moving to microservices. Microservices give us a lot of benefits, not least of which is that they make it so that we can have smaller teams focused on individual deliverables that can be delivered independently of other parts of the organization. This gives them a greater autonomy and gives them the ability to respond more efficiently, more readily to changes in the ever-growing, ever-changing marketplace. But that said, they do imply some complications because you're building distributed systems and you run the risk of running afoul of all the sort of fallacies of distributed computing. So what we're going to look at are just a number of things that we can do to build software that's better intended for production. So let's go to my second favorite place on the internet. Obviously, my first favorite place on the internet is production, but my second favorite place is start.spring.io. If you haven't been to production, you can begin your journey here at start.spring.io. When your children are restless and they cannot sleep, start.spring.io. When you wake up in the morning and you need inspiration before a cup of tea or coffee, start.spring.io. And if you suffer from indigestion after a long night of alcohol abuse and PHP, start.spring.io. And what we're going to do is we're going to build a new application that manages customer data, and we're going to use the latest and greatest version of Apache Maven, the build tool. We're going to use Java, but any language will work just fine. Java, Groovy, Kotlin, whatever. We're going to use the latest and greatest version of Spring Boot, and we're going to settle with the current long-term supported version of Java. You can use the Spring Boot actuator, like so. We're going to add Lombok, which is a compile time annotation processor. We're going to use the reactive support. Reactive programming in Spring is a way to build non-blocking event loop style applications, kind of like Node.js. We're going to use the H2 in-memory embedded SQL database. Now, because it's in memory and because it's embedded, it'll give us a way to embed a database that we can use for ease of demonstration. And I think that ought to do it. That'll give us everything we need to be productive out of the box. Let's hit generate. Open this up. Okay. So we have our public static void main entry point application. We're going to model data that talks to a SQL database. We're going to use an entity, an object that does that work. The object has a primary key. We signal as much with that annotation. We want getters and setters and toString and equals and hash codes and all that good stuff. We could write it by ourselves, but I'd much prefer to let the annotations do the talking. So these are Lombok annotations. They synthesize getters, setters, toString, equals, hat, all that kind of stuff. And then to persist instances of this into the database, I'm going to create a repository. A repository, of course, being a design pattern designed to insulate business logic from the tedious, soul-annihilatingly boring read, write, update, and delete lifecycle management. Okay, so command line runner. We're going to implement this method here. We're going to create a bean of type component, and we're going to inject collaborating object, right? It's something that'll implement the contract of customer repository. Notice that we haven't had to implement that interface. Spring will provide a bean or an object that satisfies that contract and give us that reference when we ask for it in the constructor. That's what this annotation signals. It synthesizes, it's another Lombok annotation, it synthesizes a constructor with one parameter, a customer repository. And so now we're going to write some names to the database. This is a reactive streams type. It's a container type for a bunch of things, right? And those things could be potentially unbounded and unlimited, etc. And so let's get some people on the Spring team. My name is Josh. It is so lovely to meet you. And I need to force it to evaluate the pipeline, and you would do that with subscribe. So subscribe. The problem is that this is asynchronous. There's no guarantee that anything that succeeds it will occur immediately after anything that precedes it. Instead, this happens on a different thread typically. So you need to use the operators. And I do have some things that need to happen in a particular order. Namely, I need to create the database table. Remember, it's an embedded database like SQLite or something like that, right? So I'm going to use DBC. And this will be the DDL and here's all the records. .find all, and I want these things to happen in order, so I'll use the operators. I'll say then this and then that, and then finally, I want to subscribe to the whole thing and print it out. So system out, print line. Okay, that's it. That's the entire initialization logic. Obviously, you wouldn't do this in a production application, but as this is a demo and it gave us a chance to kind of look at reactive programming, I felt like it was okay. So we're going to create a HTTP endpoint, customer REST controller. We'll inject the customer repository there, not the customer ER, the repository. It's going to be the customer's endpoint returning a reactive stream of customers. So here we are. And of course, as before, we'll synthesize the getters, the setters, the toString, and the hash code. Let's go ahead and start this and see what happens. Okay, there it is. It has worked. We can visit this endpoint. We've got our 8 records. Great. Now, I want to build an RSocket endpoint. So I'll go back to start.spring.io. And here, rather than using the HTTP support, I'll use RSocket. RSocket is a binary protocol that's developed by engineers at Netflix who then went to Facebook. It's designed to solve some of the limitations of HTTP and HTTP2 and gRPC and the like. It provides a full range of message exchange patterns, including fire and forget, request response, streaming, etc. It's bidirectional, so once connected, either side can initiate the conversation or ask questions of the other. It's also multiplexed, so you have one open socket that you originate at the very beginning of the application lifecycle, and that then stays open, and it can serve requests thereafter. So it's a really interesting protocol. We don't have a lot of time to get all into it, but it's well supported in Spring because it is a reactive technology. It reifies the concepts of reactive programming on the wire. So we're going to create a new service here. Here we are, orders, and we're just going to create a simple object called an order, and this is the order for our customers, right? So we're going to have customers, and they in turn will have orders. And you might argue about whether one should be a part of the same aggregate as the other or not, and that's a fair discussion. But to my thinking, you've got a customer entity, and should that customer then be deleted or tombstoned or whatever, you would still keep the order data around for revenue recognition purposes or something like that. So I don't know. I imagine these things have a separate life cycle, but it is really a design discussion, and that's not what we're here for. So controller, map, and I'm going to build an endpoint here. Customer ID. All right. So there's our orders controller. It's going to return data from this in-memory concurrent map of data, and obviously we have to put some data in there, so I'll just do that for the sake of our demo here in the constructor. We'll say for var customer ID equals 1, customer ID is less than or equal to 8, customer ID plus plus, and we're going to say var list of orders equals new array list, and we want this to be orders. For var order ID equals 1. All right, so we've got now some random data, and let's just put that in here like so. Customer ID to orders, and now when somebody looks at the data, they'll have something to look at. Great, so let's start this up. We wanted to start it on a different port. Obviously, it's not the same as an HTTP service, so we started it up on the RSocket port that we specify here. Let's restart. Okay, it's up and running. We can, just as we can curl the HTTP service that we created earlier like this, we can also use RSC to get the data from the RSocket endpoint. So 81, 81, and the route is orders, let's say 2, and the interaction type is a stream. There we go. So we have our HTTP and we have our RSocket endpoints. Let's create a gateway, and we're going to go back here to start.spring.io, and here we're going to create an API gateway. Okay. Now here we can use Spring Cloud Gateway, we can use Lombok, the reactive web support, and RSocket support. I've inadvertently created 2, so let me get rid of that. Okay, I'm happy with that. Let's go ahead and hit generate. So a gateway is just it's a place where we can address cross-cutting kinds of concerns, things like routing, refreshing, circuit breaking, security authentication, caching, etc. There's 2 things you might do at an edge service like this. You might do generic cross-cutting kinds of things, that affect all the services, all the downstream services, regardless of their particular semantics or their particular protocol. This is a great use of a API gateway. API gateways are a great place to do kind of AOP, but for the web, okay? And so what I'm going to do is I'm going to create an API gateway that when it receives a request to this host and port, which by the way will be 9999, will forward the request to localhost 8080/customers, which of course you might remember, since we just wrote it, is where our customer service lives. And that's an HTTP service. But the thing is, we can't take the incoming request that matches this predicate of /proxy and forward it to this one, because it would concatenate the request. It would try and merge the incoming request and forward it basically unadulterated to the downstream service. So what we want to do is to process the request as it arrives, and we do this with the use of filters. So set path customers, and then we send that down here. Now, these filters are where the real power of Spring Cloud Gateway lay. These filters do things like rate limiting. You can do retries. You can do circuit breakers. You can do just about everything. Add headers, modify the request body, the response body, etc., etc. So a lot of power there. There's our API gateway. We can see that in action. The other thing that you will probably want to do is to create an API adapter. So let's say I create a CRM client, and this in turn is going to talk to the downstream services. So I'll create some DTOs to represent the downstream data, the data we might get from the downstream services. These are going to look awfully familiar, and you might even extract out those types from those other services into some sort of mutual shared representation, maybe a Swagger or something like that. Okay, so string name, private integer ID. Okay, so as before, we'll use these. We got these types here, add component, order, get orders for integer customer ID. And we're just going to stub these out for the moment so that we kind of know what we're trying to do here. Sorry, not get orders, get customers. Okay, so we want to create, we want to make a call to the HTTP service. I'm going to do that using our non-blocking HTTP client, web client. And we're going to do the same for the RSocket endpoint using our non-blocking RSocket client called RSocket requester. We're going to synthesize the constructor so that we can have some place for the framework to inject collaborating references. We need the factory. We need to vend or produce or make available instances of these types, and we can do that as more beans here. So RSocket requester, RSocket b.build. Okay, localhost 8181, and remember RSocket, when it starts up, you connect up front, right? You can do that each time. Okay. You don't have to redo it each time, rather. Okay, so we've got our HTTP endpoints, we've got our RSocket endpoint, we've got clients for both, right? So here's RSocket, there's HTTP. Now we have the ability to actually build these requests out. So this http.get.uri http localhost 8080/customers, and we're going to retrieve the data, and we're going to say body2flux customer.class. Now, this assumes, of course, naively, of course, that the downstream service is always going to be available, which is just not the case. Things could, go bump in the night, right? The internet is a dangerous place. So we have to handle failure, and we can do that by doing retries or retry when, and we can do a back off perhaps, and we can back off with a a number of seconds or something like this, etc. You can do all these. You can use these operators, and they come for free when you use reactive types. So it doesn't matter that I'm doing HTTP here and I'm doing RSocket there. It's just part of the API, part of the abstraction. And this is one of the reasons that you get more robust code by using reactive APIs. So the route is orders. The customer ID is the second parameter there. And we're going to get the data and turn it into a stream of order data. And then finally, I want to take all of that and I want to create an aggregate. I'm going to do scatter, gather, service orchestration, and composition, like so. So I'll say class, and it's just going to be a stream of customers, a stream of orders, or list of orders. All right, that's the representation. We're going to call two different services, but we don't care that one is HTTP and the other is RSocket, because at the end of the day, they're just reactive streams, and reactive streams makes it trivial for us to compose disparate data sources. So I'm going to say, give me the customers, and then for each customer, I'm going to create a tuple. Okay, so mono.zip, mono.just customer on one side, and all the orders on the other side. So customer.getID.collectList. And what that does is it gives me this stream, stream of tuples. And you can see each tuple has a type. So T1 is the customer, T2 is the list of orders. So I'm going to just put those into the custom order object, like so. And voila, right? So now we've got the entire application. Really, really easy to kind of understand. I've just made a network call, and for each one, I'm getting the customer and I'm getting the orders. But because I'm using reactive APIs, behind the scenes, this is never blocking. It's doing concurrent scattered gather kinds of service orchestration and composition, and yet you don't see a single cyclic barrier, countdown latch, or whatever. So let's go ahead and see this in action. We'll create one more component here, one more object, a REST endpoint, customer orders REST controller. And we'll say get mapping COs, publisher of customer order. And of course, we'll use the CRM client that we just created. All right, there's our injected type. And that's it, that's the thing. So let's go ahead and start this up and see what happens. Remember, we've created an API gateway and an API adapter. All right, localhost 9999 COS, there it is. There's the customer data and the orders for the customer. And of course, here's the proxy endpoint that gives us the data from the downstream. So we've looked at a number of patterns that make it easy to integrate different sources and streams of data, and to do so in a robust, retriable, convenient, consistent, and efficient way. That said, we're not yet ready for production. So one of the things I want when I, for example, go back to my customer service is I want to support observability. And that's why I added the Spring Boot actuator. The actuator are a set of managed HTTP endpoints that give me insight into the state of the application. So I can expose all the endpoints here. I can say expose them all. I want the health endpoint to show me all the details, and I want the Kubernetes probes to be enabled as well. These are great for a demo, but obviously you're going to want to lock down these endpoints, or more to the point, you want to not open them up as I just did, so that they don't spew secret sensitive information. They're good for our purposes, however. So localhost 8080/actuator. And you can see we've got a number of different endpoints: beans, caches, health. The health endpoint gives us a set of, it gives us a listing, an enumeration of all the subsystems that may imperil our service's overall health. You can also see that we've got two probes that correspond to Kubernetes' concept of a liveness probe, which is to say, is the service still alive? And a readiness probe, which is to say, is the service able to respond to be put into traffic, right, and to be put into production. If the service, if any of those endpoints, the health or the probes, should ever return false, or if you wanted to have a custom probe, you very easily could, then Kubernetes would eventually decide, okay, well, it needs to kill that pod and then create a new one. And the question is, does it kill it immediately? Or does it give you enough time to drain existing traffic and give it, to taper off your work? You can control that with, your shutdown here. So you can say instead of immediate, which is the default, you get graceful shutdown. So in this case, you'll get sig term and then some interval, which is configurable, of course, but I think it's like 30 seconds by default. And then you'll get sig kill. This makes your services more robust. The next thing we're going to worry about when we get to production is, of course, taking the software and containerizing it, right? And no, don't freak out. I'm not talking about writing a Docker file or YAML. YAML is why people leave IT. I'm not for it. Instead, we're going to use something called build packs. All right, let's go to customer service, and we're going to do Maven clean Spring Boot, Maven clean package Spring Boot : build image. This is going to kick off the pipeline that uses Paketo to build a container. Now, because we're doing a native image and because this is a very resource intensive thing, this takes about 5 minutes because it's going to recompile not just our source code, but all the bytecode that's on the class path, which is typically what we consider the binary for the application. It's going to then turn that all into in this case, x86 machine code or whatever your platform is. All right, our build is completed. Now let's run this and see what that looks like. The benefit of this container technology is that we've built a native image which will start up in much, much faster time. You can see that most of my services take a second or less to start, but still around a second, right? With this, however, now that it's been converted to a native image, we can start it up in a mere fraction of that. I want to thank you so much for joining my talk today. I hope you got something out of it. Hope you're all doing well. Stay healthy. Thanks so much for watching.